Guys, this is dark and it has huge mass and it's small. That's 3 smoking guns right there, implicating a supermassive black hole. Space can be scary to think about. The dangers that lurk within the vast expanse of space can be terrifying. And while this applies to the entire concept of space exploration, the one part of it all that has always been intriguing and terrifying at the same time has been black holes. These beasts of power have been the subject of countless researches all across the globe. Scientists have been trying to figure out just what black holes really are and what lies in them. But all of that changes now. Neil deGrasse Tyson just revealed something huge, and our black hole is less massive than the one in the center of the Andromeda Galaxy, our nearest big galaxy. So we have black hole envy, I think we do. Music. We finally see what's inside a black hole, and well, all of it might just blow your mind. So, join us as we take you on this intergalactic journey and answer one of history's most asked questions ever. What is a black hole? Created from a massive explosion, the black hole's mass is concentrated in an incredibly small region, creating a gravitational force so intense that nothing, not even light, can escape from it. Once something is in there, it's going to stay in there forever. These forces of energy come in various sizes, ranging from stellar black holes, which can be a few times the mass of the Sun, to supermassive ones that exist at the centers of galaxies and can have millions or even billions of times the mass of our Sun. Scientists have observed the effects of black holes indirectly for decades now, and with every piece of data, we uncover hundreds of secrets. Even though it seems like they're so massive and powerful that they can't possibly have an origin story, it does. Black holes don't just exist in space. They're created. They need the remnants of massive stars that have exhausted their nuclear fuel to be born. These stars undergo a supernova explosion, a spectacular event that marks the end of their lives. During a supernova, the outer layers of the star are violently expelled into space while the core undergoes a gravitational collapse. But not all collapses are going to be the same. If the core's mass is several times larger than that of our Sun, the force of gravity overwhelms all other forces, causing the core to collapse inward. This collapse is so intense that it compresses the mass into an incredibly small volume, creating an object with a gravitational field so powerful that nothing will be able to escape its grasp, thus creating a black hole. The size of a black hole is determined by its mass. Stellar black holes, which are the most commonly known type, have a mass range from a few times to several tens of times that of our Sun. At the core of a black hole lies the singularity, a region of infinite density and space-time curvature. According to our current understanding of physics, the laws of nature break down at this point, and our conventional theories cannot fully explain what happens within the singularity. To truly understand the nature of singularities, we would need to think outside the box a little. In the world of physics, a singularity refers to a point in spacetime where certain quantities become infinite or undefined. These singularities appear in various theoretical contexts, such as at the beginning of an expanding universe, which is commonly known as the Big Bang singularity, and within the inside of black holes. When we study the Big Bang singularity, a fundamental challenge comes forward. According to the theory, the universe originated from an extremely hot and dense state about 13.8 billion years ago. But as we rewind time toward this initial state, the equations of general relativity, which govern the behavior of gravity, break down. This breakdown implies that our current understanding of physics cannot fully describe the conditions at the moment of the Big Bang. Resolving this issue requires a theory that combines general relativity with the principles of quantum mechanics. You see, black holes contain singularities at their cores. These are regions where the gravitational pull becomes infinitely strong, and spacetime is highly curved. According to general relativity, matter and energy that fall into a black hole reach its singularity and become infinitely compressed. This concept too is beyond our concepts of physics, adding to the problem here. The challenge of singularities has motivated scientists to search for a theory of quantum gravity, which aims to unify the principles of general relativity and quantum mechanics once and for all. So, there's at least a little bit of clarity here. Quantum gravity seeks to provide a framework that accounts for the behavior of spacetime on both cosmic and subatomic scales. A theory like this could potentially offer insights into the nature of singularities and how the universe really works. One approach to addressing the issue of singularities is the theory of loop quantum gravity. This theory suggests that at extremely small scales, spacetime is quantized, meaning it consists of discrete, indivisible units everywhere. These fundamental units are often referred to as loops or spin networks. In loop quantum gravity, the concept of quantization is applied to spacetime itself. This means that spacetime isn't considered as a continuous and infinitely divisible entity, but rather as a collection of discrete elements. These discrete units of spacetime are often seen as interconnected loops or networks that represent the underlying structure of the fabric of the universe. Within the framework of loop quantum gravity, singularities associated with black holes and the Big Bang could be resolved. One of the key insights of this theory is that at extremely small scales, the discrete nature of spacetime prevents the occurrence of infinite densities and curvatures that give rise to singularities. In classical general relativity, for example, in the context of black holes, loop quantum gravity suggests that as matter collapses toward the core, the spacetime fabric becomes increasingly tiny. The size prevents the matter from reaching an infinitely dense singularity. Instead, the collapsing matter encounters a quantum bounce near the core, where it rebounds and begins to expand again. This scenario leads to the formation of a new spacetime region inside the black hole, often referred to as a quantum black hole or a bounce stellar black hole. The bounce region replaces the classical singularity, allowing for a resolution of the singularity problem. Similarly, in the case of the Big Bang singularity, loop quantum gravity proposes that the universe's initial state was not characterized by an infinitely dense and singular point. Instead, the universe emerged from a pre-existing quantum gravitational phase, where the nature of spacetime prevents the occurrence of a singularity. This provides a new perspective on the origin and evolution of the universe, avoiding the singularities present in classical models. The search for a unifying theory is driven by the desire to reconcile the classical treatment of singularities in physics with the principles of quantum physics. Bridging this gap could potentially yield new insights and resolutions to the challenges posed by singularities. But then again, there are so many types of black holes that even this proposed solution gets left behind. Stellar black holes are the most commonly observed type of black hole in the universe. As we've briefly touched upon earlier on in this video, they are formed through gravitational collapse at the end of a massive star's life. The way all of this works is, once a massive star has consumed all its nuclear fuel, the outward pressure generated by nuclear reactions can no longer counteract the force of gravity pulling inward. The gravitational force becomes dominant, causing the star to collapse under its own weight. This collapse results in the formation of a stellar black hole. But as the star collapses, it becomes incredibly compact, packing a significant amount of mass into a very small volume. As a result, stellar black holes typically have a mass ranging from a few times to about 20 times that of the Sun, although despite their mass, they have remarkably small sizes. Their diameter is only a few kilometers, which just goes to show how extremely dense they are. The immense density of a stellar black hole leads to the formation of an event horizon, a boundary beyond which nothing, not even light, can escape. This event horizon marks the point of no return, where the gravitational pull of the black hole becomes so strong that any object or information that crosses it is trapped forever within the black hole. Then we've got intermediate mass black holes. While the precise mass range for intermediate mass black holes is still something scientists need to put through more research and refinement, they are generally thought to have masses ranging from thousands to tens of thousands of times that of the Sun. So that would be much denser than a stellar black hole. The formation mechanisms of intermediate mass black holes are still not entirely understood, but there are two primary scenarios that are currently being investigated. The first possibility is that they form through the merging of multiple stellar mass black holes in regions of space with a high concentration of massive stars, such as globular clusters or galactic nuclei. Interactions between stars can lead to the formation of binary systems. Over time, these binary systems can merge because of gravitational interactions, eventually resulting in the creation of an intermediate mass black hole. The second formation scenario proposes that intermediate mass black holes form through the direct collapse of massive gas clouds in the early universe. These gas clouds, which are dense regions of primordial matter, can undergo rapid gravitational collapse, leading to the formation of an intermediate mass black hole instead of a star. This process may have been more common in the early stages of galaxy formation when gas concentrations were higher, which is why stellar black holes are a lot more common now. One of the main things about intermediate mass black holes is that they're extremely challenging to detect because of their mysterious nature and the limited number. However, their presence has been detected through indirect means, such as studying the dynamics of stars and gas near these potential black holes. Not only that, but recent observations have provided some evidence for the existence of intermediate mass black holes in galactic nuclei too, so they might not end up being as sparse as we have always thought they were. Supermassive black holes are the big guns of the black hole family, with masses that range from millions to billions of times that of the Sun. These colossal beasts occupy the central regions of most galaxies, including our own Milky Way. They hold significant gravitational sway over their galactic surroundings and have a profound impact on the evolution of galaxies. The formation of supermassive black holes remains an active area of research and is still not fully understood. But even then, lots of different theories have been proposed to explain their origins. One prominent hypothesis suggests that supermassive black holes evolve from smaller black holes through a process called accretion. According to this idea, as matter such as gas, dust, and stars accumulates around a black hole, it forms a swirling disk known as an accretion disk. The black hole's immense gravitational pull draws material from this disk, causing it to spiral inward and ultimately merge with the black hole over vast periods of time. This continuous accretion of matter allows the black hole to grow to a supermassive scale. During the accretion process, enormous amounts of gravitational potential energy are released as the matter falls into the black hole. This released energy powers some of the brightest and most powerful phenomena in the universe. But away from all of that are charged black holes, which represent a fascinating variation of black holes characterized by the presence of an electric charge. There are two main types of charged black holes: Nordstrom black holes and Kerr-Newman black holes. Each type exhibits distinct properties that are formed from the relationship between the black hole's charge and other factors such as rotation. Nordstrom black holes are charged but non-rotating. They are described by the Nordstrom solution in the framework of general relativity. The charge of these black holes affects the behavior of their gravitational field. However, in terms of their overall structure, Nordstrom black holes are similar to uncharged black holes. They possess an event horizon, but the size of the event horizon for a Nordstrom black hole depends on both its mass and electric charge. On the other hand, Kerr-Newman black holes are charged and rotating. They are described by the Kerr-Newman solution in general relativity. The combination of electric charge and rotation introduces unique phenomena associated with these black holes. One of the notable effects is called frame dragging, which occurs because the rotating black hole drags and twists the surrounding spacetime. Kerr-Newman black holes have both an event horizon and an inner region known as the Cauchy horizon. This is an inner boundary within the black hole that separates the exterior region from the region where the singularity is located. The properties of the Cauchy horizon are influenced by the black hole's charge and rotation, and they contribute to the intricate dynamics near the center of the black hole. At the Cauchy horizon, the effects of the black hole's charge and rotation become significant. The Cauchy horizon is associated with a problem known as the cosmic censorship hypothesis, which is a conjecture in general relativity. This particular hypothesis suggests that singularities within black holes are always hidden behind event horizons, ensuring that we can't see whatever effects they might have on the external universe. The behavior of the Cauchy horizon is intimately connected to the validity of this hypothesis. If the cosmic censorship hypothesis holds true, the Cauchy horizon would remain hidden within the black hole, and its intricate dynamics wouldn't be observable from the outside. So, to say that it's important would be an understatement. But there's another side to them as well. Unexplored and hypothetical black holes present interesting avenues for scientific exploration within the realm of astrophysics. While the types of black holes mentioned earlier are well known, there are still unexplored frontiers in black hole research. One area of ongoing investigation is the existence of primordial black holes. These are hypothetical black holes that could have formed in the early universe shortly after the Big Bang. Primordial black holes would have emerged from regions of extreme density fluctuations, and their formation mechanism differs from those of stellar black holes. They could have a wide range of masses, including tiny black holes known as microblack holes, making them much different than any other type of black holes we usually encounter. Another fascinating avenue is the exploration of rotating black holes with extreme angular momentum. These black holes, known as extremal black holes, are hypothetical objects that spin at their maximum possible rates. They are of great interest because they push the limits of our current understanding of black hole physics. But no matter which type of black hole you're talking about, the one concept that always comes up alongside it is that of dark matter. Dark matter is a unique form of matter that takes over a significant portion of the mass in the universe, far surpassing the amount of ordinary matter that we can directly observe. It's called dark because it doesn't interact with light or other forms of electromagnetic radiation, making it difficult to detect and study. Its presence is actually detected from its gravitational effects on visible matter and the large-scale structure of the cosmos. While the exact nature of dark matter remains unknown, several theories suggest that it played a crucial role in the formation and evolution of galaxies, including the formation of black holes. One theory here proposes that dark matter acts as the scaffolding, and galaxies assemble on it. Its gravitational pull helps gather ordinary matter such as gas and dust, leading to the formation of massive structures like galaxies. As these structures evolve, they can eventually give rise to the conditions necessary for the formation of black holes. Dark matter, through its gravitational influence, plays a fundamental role in shaping the distribution of matter in the universe and creating the right circumstances for the formation of black holes. Another possibility is that dark matter itself could be composed of primordial black holes.